Okay, so I want to tell you about Willy's descendants and the search for charge symmetry breaking, which I will abbreviate from now on as, abbreviate from now on as CSB. So it's applying Willy's lessons about the importance of spin observables, careful control of systematic errors, and advancing the technical state of the art to symmetry principles other than parity, which is what the remaining talks in this session will also be about. So this particular search is not one in which Willy himself was involved, but he must have passed along the genes because this is what I call CSB neology. Among Willy's stable of graduate students in the late 60s and early 70s, there was myself and Lynn Knudsen and Ed Stevenson. Actually, Scott Wissink was not a student of Willy's. He was a student of Stan Hanna at Stanford, but he did his thesis experiment working with Willy. So these were all sort of second generation folks. Lynn had a graduate student, Jim Sawinski, who's here. Jim was also involved in all this. Lynn and I proposed an experiment at IUCF to test charge symmetry, and I'll talk about this later, by doing polarized neutron, polarized proton scattering. Jim Sawinski was heavily involved in that, and so was Scott Wissink. Ed Stevenson then later proposed a different approach to charge symmetry, which involved looking for a forbidden reaction. Deuteron goes to alpha and pi 0. Then my graduate student, Ili Korkmaz, and Scott's graduate student, Alina Opper, jointly proposed yet another approach to charge symmetry in an experiment at Triumph, which involved looking for a deviation from 4-aft symmetry in the reaction neutron-proton goes to deuteron pi 0. So there was really a genealogical chain here, and I'm going to talk about those 3 experiments. So first, what is charge symmetry? At the basic level, it's the invariance of the strong interactions and color forces under the interchange of up and down quarks. So you simply change all up quarks or up anti-quarks into down quarks or down anti-quarks. So it's the simplest form of quark flavor symmetry, and it's vital for nuclear physics. It's clearly not preserved by the electromagnetic interactions because the up quark has a charge of plus 2/3 of the electronic charge, and the down quark has a charge, an electric charge of minus 1/3 times E. So they have different electric charges, different magnetic moments. So it's not satisfied by the electromagnetic interaction. And in order to test it, the importance is to try to isolate the strong interaction effects from the electromagnetic effects. It's also violated, though, as it turns out, by the fact that the up and down quarks have different masses. And that mass difference, as it turns out, is essential for life in the universe. So if the electromagnetic violations were all there were, the proton, which has 2 up quarks, which have twice the charge magnitude of the down quarks, would have more electric repulsion from the up-up interaction than the neutron, its charge symmetric mirror, would have from the Coulomb repulsion of the 2 down quarks. So if the electromagnetic violations of charge symmetry were all there were, the proton would have more repulsive energy and therefore a higher mass. The proton and the hydrogen atom would be unstable, and none of us would be here. In fact, the stability of the hydrogen atom requires that the mass of the neutron be at least equal to the mass of the proton and the mass of the electron. That requires that the neutron be at least 0.05% heavier than the proton. On the other hand, stellar fusion, which produces the energy and the elements for life, the first step in stellar fusion is pp fusion, producing a deuteron, a positron, and a neutrino. So you get a proton changing into a neutron. If the neutron were too much heavier than the proton, That reaction would not occur. We wouldn't have efficient stellar fusion. We wouldn't have the energy for life. That requires that the neutron be no heavier than the proton by 0.19%. So in fact, there's a narrow window that nature has to fit into in order to support life in the universe. Fortunately for us, it does fit in that window. The neutron is actually heavier than the proton by 0.14%. And we now know that's because the down quark has about twice the mass of the up quark, which I'll come back to later. So the object of these experiments was to see how that up-down quark mass difference is manifested in charge symmetry breaking nuclear forces. So the more traditional way of trying to do that was to compare neutron-neutron to proton-proton scattering, but that's really complicated. First of all, because the proton-proton case has an enormous Coulomb effect at low energies, which you have to subtract out. But also it's really hard to do neutron-neutron scattering. You have to do it by final state interactions in three-body systems, and that has various experimental difficulties. So Lynn and I proposed an experiment. Lynn came to me with this idea when we were both young faculty members. We proposed an experiment at IUCF, which would use spin observables in the scattering of polarized neutrons on polarized protons, where you don't have any Coulomb interaction. There is an electromagnetic effect, which is spin-orbit coupling of the sort that Tom talked about yesterday. It's basically the interaction of the neutron magnetic moment with the magnetic field set up by the passing proton. But that's a much weaker effect than the Coulomb scattering, and that's smaller than the effects we'll be searching for, as you'll see. So basically, this experiment that Yusuf Magdizi talked about yesterday of calibrating the proton beam polarization at RIC works because the beam proton and the target proton are identical particles. So the analyzing power associated with beam spin flip has to be the same as the analyzing power associated with target spin flip. The same thing is true for NP to the extent that the neutron is really the same as the proton under charge symmetry for the strong interaction. Or to show you a diagram sort of along the lines of the things that Krishna showed you, if you have a neutron with spin up scattering from a proton in the center of mass and you detect the neutron at angle theta, you apply charge symmetry, you change the neutrons into protons and vice versa. You then have a neutron scattering from a proton, but now it's the proton which has spin up and going out at angle theta. So the net result is the analyzing power associated with neutron beam spin flip has to be equal to the analyzing power associated with proton beam spin flip. And if there are differences, we hope those can be related to the up-down quark mass difference. So the problem was some assembly was required at IUCF. Willy wanted each of his graduate students to master all parts of every experiment. And you had to do each part carefully. If you made dumb mistakes, you tended to get this stare of incredulity, which we wanted to avoid. So we followed his lead here. We tried to do everything ourselves and succeeded eventually, but it took a decade.
Seriously? A decade?
It took a decade, yeah. So I'll explain to you why here. So, first of all, we didn't have a polarized neutron beam at IUCF, so we had to produce one. We had to build a polarized neutron facility, which involved taking our polarized proton beam at 200 MeV from the cyclotron, doing a charge exchange reaction on a 20 centimeter thick liquid deuterium target. And if you do that charge exchange at 10 degrees, there's a large polarization transfer from the proton to the neutron, but you have to do it in a vertical scattering plane. So we bent the proton down by 10 degrees and eventually buried it in a beam dump under the floor. You get polarized neutrons out, sweep away scattered protons, put it through a thick collimator to collimate the neutrons, had to build a polarized, a cryogenic polarized hydrogen target from scratch and put it through detectors that we had to build from scratch. The detectors, you had to detect the neutron and proton in coincidence in a left-right symmetric detector array. And they had to, both arms, be sensitive to both neutrons and protons and give you angle information on both the proton and the neutron. So it involved also big neutron detectors, which were huge vats of liquid scintillator subdivided into a lot of optically isolated cells. You needed, in order to be interesting, you had to measure the difference between the neutron and proton analyzing powers to a part per thousand. And the complication is what you really measure are beam and target asymmetries, which are the product of polarizations times the analyzing powers. And we couldn't really know the polarization of the beam and target to the required precision. So we worked near 90 degrees in the center of mass, where the average analyzing power is 0. And then it turns out the beam and target polarizations are not so important. You're basically looking for an angle shift in the zero crossing between the neutron and proton analyzing powers. Here's a picture when it was nearly done. This is Will Jacobs, who was essential to this experiment. Will is not a Willy student, but he grew up in Madison. He actually grew up in the first Usonian house that Frank Lloyd Wright designed for a family out in Middleton. So he's an honorary Badger. This is the left-right detector, symmetric detector arms that you can see. The polarized target is a Dewar over here dismounted. It usually goes right here, so it's in the beam. We were all a lot younger then. That's me in our electronics counting house. This polarized target, which was Jim Sawinski's thesis experiment. So Jim and Lynn developed this. This was a novel target that I don't have time to talk about in detail. But basically, the target material was ytterbium-doped yttrium ethyl sulfate, which you then rotated in a magnetic field to polarize the protons in the hydrogen atoms. The problem is there are 9 times as many protons bound in all the contaminant nuclei here as there are free protons from hydrogen atoms. So you had to distinguish between the free scattering of neutrons from free protons against the quasi-free scattering of neutrons from all the junk protons that were bound inside nuclei. And the way you do that is by the angular correlation, which is sharp for the two-body scattering on free protons and smeared out by the Fermi motion of the protons as they're bound inside nuclei. So that's why we needed to measure both the neutron and proton with good angular resolution. This is what our opening angle between the detected neutron and proton distribution looked like raw before cuts, and then after various cuts to look at, make sure we were looking at protons and other ways consistent with free scattering. This is a log scale, so you see the big peak here from free scattering and a smeared background from quasi-free scattering. We designed a dummy target which mocked up all the junk in the polarized target without hydrogen, at least without hydrogen at the beginning, but in humid Indiana summers, the target absorbed some water over time. So you see a little hydrogen peak even from the dummy target. So you subtract that. You had to measure the asymmetries in slices of beam energy, which you did by RF timing against the cyclotron, because the neutron beam polarization varies with energy. And you can see that here. These are the measured asymmetries, the target asymmetry in open squares, the beam asymmetry in the dark squares for 3 different energy slices. And the analyzing power is not varying rapidly, but the ratio of beam to target asymmetry is varying with energy because the beam polarization varies with energy. So it was important to do that in energy slices. Eventually we got to publish the results. We had 9 hardy collaborators that saw it through for 12 years to publication. That was a third of the collaborators of a competing Triumph experiment, not because of bravado, but because of the naivete of young faculty members who underestimated the task at the beginning, and a long paper that was hopefully written with a precision of which Willy would approve. Not that I sent it to him for approval, as he taught us in the pre-P parity experiment, there was a long table of systematic error budgets, which I won't go through, but every line in there required a detailed analysis. This was our result. So in fact, the systematic errors at the end were smaller than statistical uncertainty. And this is the difference between the neutron and proton scattering analyzing powers. It's a few part times 10 to the minus 4. So it's a small effect, but what you get from the electromagnetic spin orbit is down here. So we clearly saw strong interaction charge symmetry breaking. This is the Triumph experiment, which actually got published before ours, but has significantly larger uncertainties, and it's at a higher energy. But both experiments saw charge symmetry breaking in the strong interaction. In the IUCF experiment, we actually also provided information on the angular dependence of the charge symmetry breaking, which is shown here. And the solid line are actually predictions for both angular dependence and magnitude that were done not through direct QCD calculations, but through meson exchange, estimating what the impact of the up-down quark mass difference should be on various meson exchange terms. So that all agreed fairly well. Whoops. What happened here? Try that again. Yeah. Okay, so the results agreed well with predictions based on meson exchange models of the nuclear force, but perhaps it's calculable directly from lattice QCD in the not too distant future, and I'll come back to that in a few minutes. Yeah, this is just not advancing anymore. Yeah, thank you. So Ed Stevenson's independent experiment was to search for charge symmetry breaking via a forbidden reaction. The deuteron is a self-conjugate under charge symmetry. It turns back into itself because it has one neutron, one proton. Same for the alpha particle. But a pi zero, which at the quark model level is UU bar minus DD bar over the square root of 2. If you apply charge symmetry, you get a sign change. So the pi zero is an eigenstate of charge symmetry, but it's an odd eigenstate, whereas the deuteron and the alpha are even eigenstates. And therefore, the reaction is forbidden because the entrance channel is an even charge symmetry eigenstate, and the exit channel is an odd eigenstate. And this experiment used a lot of clever features of the IUCF cooler. There was a section where there was a 6-degree bend in the proton beam that was stored in the cooler ring, or the deuteron beam in this case. And the alpha particles have less magnetic rigidity, so you could turn them away from the circulating cooler beam. And if you do the experiment right above threshold, those alpha particles are all focused in a very narrow forward cone. So you can collect them all in a magnetic channel and focus them on detectors at the end of that channel. You can surround a deuteron gas jet target, so it's a pure target, no contaminants, with lead glass to detect both gammas from the pi zero decay. So you detect the alphas in coincidence with both gammas. 5 minutes, okay. You go advance, sorry. And this was the result. They saw clear indication of this charge symmetry forbidden reaction. The only background was in fact a physics background that comes from the second order electromagnetic interaction where deuterons collide and produce an alpha particle and two photons that are not from the pi-0 decay. And they measured the cross sections. You advance. Alina and Willy Korkmaz decided to test it by looking at 4-aft asymmetry, and neutron-proton goes to d pi-0. So if you do a similar diagram to what I showed you before for the polarization experiment, you basically predict that deuterons coming out at an angle theta should have the same cross-section as those coming out at an angle pi minus theta. So they looked for, thank you, they looked at triumph in a near threshold experiment just by detecting the deuterons from pi-0 production at far forward angles in the lab frame and advance. And you see then a locus where you can measure the deuteron momentum versus the deuteron laboratory angle. You get a nice kinematic locus. The higher momentum deuterons are the ones that are forward in the center of mass. The lower momentum deuterons are the ones that are backward. And you try to measure the 4-aft asymmetry from there. Okay. And this was their result. They again saw something on the order of a few parts in 10 to the third. And there are predictions all over the map of the right order of magnitude. The meson exchange calculations or chiral effective field theory calculations here had more diagrams and more uncertainties. But again, they saw clear indication of strong interaction charge symmetry breaking. So this is all the past. I wanted the talks in this section to talk a little bit about the future as well. So on the theory front, I am hopeful that it's not too far in the future when lattice QCD can provide a unified framework for tying all of those charge symmetry breaking observables more directly to the up-down quark mass difference. There have been recent lattice QCD proof of principle calculations which have attacked the neutron-proton mass difference, including the up-down quark mass difference, nucleon-nucleon scattering in partial waves from 0 to 3, evaluation of the expansion coefficients in chiral effective field theory, and few body reactions. These are the needed ingredients. All those calculations are still done with unphysically large quark masses, so it just requires more computing power, but the exascale computing era is coming soon. And I'll leave you with an experimental challenge. You get the feeling here that we're looking through the wrong end of the telescope. If you look, yeah, go ahead. If you look at the quark level, the up-down quark mass difference, one more, the best information we have right now, we can't isolate quarks, but the up quark mass seems to be about 2.2 MeV, the down quark mass about 4.7 MeV. So the mass difference divided by the mass sum is 36% at the current quark level, and yet all the effects we're looking at are, you know, on the order of a part per thousand or smaller. The reason for that is that the denominator in that ratio is affected by chiral symmetry breaking, mainly the transition from current quarks to constituent quarks inside the nucleon. So that denominator grows a lot. Unfortunately, the numerator does not grow and you get very small effects. So the question is there some experiment where you can look for something at the current quark level of tens of %? The answer is yes, but it ain't simple. The pion is the Goldstone boson that is associated with the breaking of chiral symmetry. So its mass and some of its scattering properties are deduced directly from the current quark masses, not from constituent quark masses. Weinberg already pointed out in his seminal paper about chiral symmetry breaking back in 1977, and subsequent theoretical calculations by Van Kolk and more recently by Fett and Meissner have shown that there is a charge symmetry breaking effect at something like the current quark level. But what you have to do is compare low energy pi-0 neutron to pi-0 proton scattering. And then you can get near threshold on the order of 30% effects, according to theory. So the challenge is how you do those experiments. I'll just give you a hint because I'll skip a couple of slides. But for pi-0 neutron, you have to look for a final state interaction, which you can do in lambda decay by measuring a time reversal odd polarization effect, because that occurs only by virtue of the final state interaction. And it's a tricky experiment, but it's probably doable in the future. Now skip a slide. So this is just illustrating that experiment that I don't have time to talk about and how to do it. But yeah, a quick summary: the quest to understand in detail how charge symmetry breaking in few body systems can be directly related to the up-down quark mass difference is a continuing saga. I hope the theory will advance to the stage of lattice QCD calculation soon. And finally, it's been fueled by techniques and care that Willy taught us, and by what is really his greatest legacy, which is the scientists he trained and the ones trained by them. And we can only hope that we have helped to extend his legacy. So, thank you.
Thank you very much for a very clear, very interesting talk, Steve. I'm sure there are questions. Len, you know that a photo of you was shown right before you walked through the door.
Ah, okay. I didn't notice that you weren't there.
I just have a comment. You mentioned the TRIUMPH charge symmetry breaking experiment. My understanding is that that experiment was proposed by Rachel Plattner, who was, of course, also a Wisconsin person who was a postdoc here with Willy when I joined the group in '68.
So that's very, I did not know that. So, aha.
I'll tell you about a really good experiment if you include me on the paper.
Okay, great. So even more of a Willy connection.
More questions? Yes.
Paul Pansella. Just a comment again. Thought probably it should be said it was my privilege to work on the DD alpha pi-0 experiment, which you didn't mention part of the bittersweet significance of it. And Ed can correct me if I'm wrong, but that's the experiment where the last piece of hardware on the cooler failed before we quite finished. And that was the end of the cooler experimental program.
Yeah, so that along with Pintex and another experiment we're not talking about were sort of the final year of cooler operation. It was a challenge to get all those technically complex experiments done as the money was running out.
Yeah, Ed Stevenson here. Just to elaborate on Paul's point, what happened was that the magnet that we used to extract the helium beam from the ring was a very high intensity magnet with a very sharp field boundary. And that was achieved by George Berg magnet design, which involved a very tightly wound set of coils running rather high current. And that's what actually failed during the last week of the experiment. Somehow or another, as fate would have it, the copper tubing itself broke a leak, and water was spraying around the experimental area when we got down to it. So we turned off the water, but that provided us an opportunity of having a few days. I talked to Barbara, who's here, and she was willing to come down and turn on Pintex for us so that we could actually do a confirmation of the target density and calibration of the DD to alpha pi-0, because we were doing deuteron-deuteron scattering in order to get the cross section. So that normalization was an essential piece of the experiment. And I want to thank the Pentex crowd for saving us at the very last minute, because that was really the end of the cooler ring as well.